Okay, so up until this point, we've been finding areas between two curves, and each curve in those examples that we've covered have been given where y is a function of x. And that's typically what we look at the most in like algebra and calculus is functions where y is given as a function of x. Or in other words, x is an independent variable and y is a dependent variable. But there's no solid reason as to why that should always be the case. In fact, sometimes it's more convenient to think of y as your independent variable and x as your dependent variable. In which case we would be thinking of x as a function of y. And in those cases, we get curves kind of like the ones shown here. So I have x equals g of y, giving me this blue curve, and x equals f of y, giving me this red curve. And I may want to find the area between those two curves. In this case, we kind of have to flip around everything that we're thinking about. So the functions, x being given as a function of y, that's the first thing that sort of flips. But then where we're finding that region is also kind of being flipped around. Previously, we were looking at regions over some interval on the x-axis because the x was the independent variable in those examples. If y is going to be our independent variable now, we're going to be looking at intervals on the y-axis where we're going to get the bounds for our region from. Okay, so we can go through a similar derivation that we did before, where we could find this area by constructing rectangles over little subintervals that we cut this interval on our y-axis CD up into. Over each of those little subintervals would give us kind of the base of all of these rectangles, and then we need to find the heights of these rectangles. Well, if you take a look at this one little rectangle right here, I want to find the height of that rectangle, which is interpreted as the length of that dashed line right there. And remember, we need these answers to come out positive. So that height I have to interpret as a positive value, which means I should take the highest point and subtract the lowest point. Now here I'm using the terms high and low, but neither this point nor this point are higher or lower than the other. Really, I should be saying greatest and least, or largest and smallest. So because these are, we're looking at x values to determine the length of this thing, this x value minus this x value, for example, then whichever x value is furthest to the right is going to be the largest of those two. So what that tells me is that when we get to the point where we use an integral to compute this area, we need to look at the curve that is furthest to the right and set that first, and then subtract the function that is furthest to the left. That's the g of y down there. So I'm going to think of this as right minus left for these problems. Okay, let's do an example. So here it says find the area of the region bounded by the curves 4x plus y squared equals 12 and x equals y. Now here I could think of that as either x as a function of y or y as a function of x. I could say that's the same thing as the line y equals x instead of x equals y. But here it's not immediately apparent which variable I should be thinking of as independent, which one I should be thinking of as dependent. And I can say that for this, it is a little bit easier to solve for x than it is for y. Because if I were to try to solve this for y, it would involve taking a square root. And I know that if I take square roots of both sides of an equation, I have to include a plus or minus, and that makes things complicated when we're trying to integrate stuff like that. So instead, let's solve for x. That would involve subtracting the y squared to both sides and then dividing everything by 4, which would give me x equals negative 1/4 y squared plus 12 divided by 4 would be 3. Okay? Let's graph these now. How do you graph these functions? Well, the right one is the easiest one. Remember, x equals y is the same thing as y equals x, which is this line right here, right? I'm not worried about it being super accurate. Again, I just need it to look roughly like the correct line. What does this look like, though? Oh, I just realized my y, I wrote it like an x. It should be a y. It's a quadratic, right? It's got a y squared term in it as a polynomial, and that's the highest degree term. That's definitely a quadratic. We know that those look like parabolas. However, because it's y squared showing up in there, not an x squared, this is a parabola that's going to open horizontally instead of vertically. Not only that, because I have a negative leading coefficient, this is going to be a parabola that opens towards the left as opposed to the right. Okay? In addition to that, I have this +3 here, which tells me that the x-intercept for this parabola, which is also going to be its vertex, happens right here at the value 3 on the x-axis. So putting that information together, my parabola should do something like this, right? And I want to make sure I draw that far enough out so I can see a point of intersection there. Okay? Notice it does not say find the area between these two curves over the interval something something. It's just saying the region bounded by the curves. That means, like that other example we did previously, I need to determine what this interval is right here. Right? So from here to here, I can see is where this region is bounded. And again, remember, because we are looking at x as a function of y in both cases, x equals y here, x equals -1/4 y squared plus 3 here, I have to think of these as, I have to think of my interval as being on the y-axis, not on the x-axis. Okay? So a couple of things we need to do before we can start to integrate. First thing is we should determine what the y values of these points of intersection are. And I can do that like I did previously. Set the two functions equal to each other and then solve for y. So I have, once I have solved for x here, I got -1/4 y squared plus 3. So if I were to write -1/4 y squared plus 3 and set that equal to the other function, which is just y, I can solve this equation for y. Let's move some terms over. So I'm going to get 0 equals 1/4 y squared plus y minus 3. I don't like that 1/4 there, so let's multiply both sides of our equation by 4 to eliminate that fraction. I still have a 0 there. This becomes y squared plus 4y minus 12, which factors really nicely. I'm going to get y minus 2, y plus 6, which gives me y equals 2 or -6. Those are going to be these two y coordinates here, and those will also be the limits of integration that I use. So now let's set up our integral. Integral from -6 to 2, that's the interval we just found. Now I need to subtract my functions. So I need to figure out which function shows up first, which shows up second. And remember, for these types of curves, you go right minus left, not top minus bottom. So the rightmost function is the parabola. -1/4 y squared plus 3 minus the leftmost function, which is the line. That's just minus y. Okay? Notice I didn't put parentheses around either function because really the one that matters is the second function, and it only had one term. All right, this is straightforward to integrate. So again, it's a polynomial. These are the easiest things to integrate, generally speaking. So I have -1/12 y cubed plus 3y minus y squared over 2. And we go from -6 to 2. Okay? You're going to see that as I do more and more examples in this class involving definite integrals, I'm usually going to take it up to maybe about this point. But then I'm going to go right to a solution. I'm going to go right to an answer. I have to go to my notes and find where I wrote that. This one came out to 280 thirds, I believe. Yeah. Now, the reason I'm doing that is because the work that follows from here is arithmetic. Remember, you're plugging 2 into all of these, minus whatever you get from plugging -6 into all of these. Most of you are probably going to use calculators for that. I do encourage you to try that by hand sometimes. It's good practice, but it's not worth the time for me to do that every single example. So just understand that I may be jumping from here to an actual value in a lot of examples throughout this class. Okay? Here's our very last problem here, and it's going to tie in something that we haven't talked about in this section yet, but you would have talked about in Calculus 1. It says it says the widths in meters of a kidney-shaped swimming pool, this was shown here, were measured at 2-meter intervals, as shown below. Use the midpoint rule to estimate the area of the pool. If you don't remember the midpoint rule, in Calculus 1, we talk about the midpoint rule as an approximation method for approximating an integral. And so if I return here for a second, the beginning of this section, remember that the definite integral is something that we can approximate with these rectangles, where the height of each rectangle is determined by choosing some sample point in every single one of these rectangles. In this example, we used right endpoints. The midpoint rule says that if we choose those sample points to be the exact midpoint of each one of our subintervals, we end up getting a fairly good approximation. And what I mean by fairly good can be made mathematically precise, but we're not going to do that here. So what we're going to do is imagine approximating this area here using rectangles, but we're going to use rectangles like this, where the areas, or sorry, the heights rather, are found by choosing as the midpoint the points that are giving us these measurements. It would kind of look like this. Okay. Now, why is this problem showing up in this section as opposed to Chapter 5, where you learn about the midpoint rule? And it's because you can think of the height of each of these rectangles as being found by locating a point on some top function, which is like this top curve up here, and subtracting some bottom, the point on some bottom function down here. So it's kind of like finding an area between two curves if you think of this as a top curve and this as a bottom curve. But really, like, to find this, there's not a whole lot of work to do. It's all arithmetic, really. So remember, first of all, that the width of each one of these rectangles is 2 meters, because we're told that here. These are measured in 2-meter intervals. So if I want to find the area of each rectangle, I would take the height, 6.2 if for this one, multiply it by 2. And then I'm going to add to that the height of the next one, 7.2 times 2. And then 6.8 times 2. And so because each one is being multiplied by 2, we can factor that 2 out to save ourselves a little bit of time. And then add all of the heights, 6.2 plus 7.2 plus 6.8 plus 5.6 plus 5.0, I'm just going to write 5, plus 4.8 plus 4.8. This one definitely put that into a calculator, work that out. This should come out to 80.8. And because we have units here, we should include them. It's area, so it'd be square meters. Okay? So that's the midpoint rule applied to a problem that you can interpret as an area between two curves. With that example, we're done with section 6.1.